Okay, so when we think of binary search, it is like in a dictionary. If you want to find out which element is there, if you want to search a word in a dictionary and you go through each page, it will take it will take a lot of time. Rather, what you actually do when looking for a word in a dictionary is that you go to a random page, you check whether the element, the number, sorry, the word that you are looking for is after this word or before this word, and then you reject the. Let's say you are looking for pet, and you the word that you reach at is dog. So you know that the word pet will come after dog. So you will not look at the pages before dog. So that's how you have like rejected the first half of the dictionary, and you know that the word that you are looking for is in the rest of the portion. So why do we in binary search, the basic theory is that you divide the entire search space into half and then reject one half. It could have been the case that you could have gone for like divided into three halves and then check which region you have to search into, or let's say into four halves and then you see that which region you need to search. But it turns out that the best way in which the least number of searches are required is binary search. That is dividing the search region into half portion and then rejecting one half and searching in the other half. Is this clear why we take binary and not ternary, like dividing into three parts or four parts? What I said is clear.
No, why don't we divide it in three parts or four parts? That would be much
Okay.
faster.
No, actually, it turns out that uh, it is slower than binary search, because what happens is that when you are dividing into two parts, you have to perform one operation, one comparison to know which region you have to look into. But uh, but when you divide it into three parts, then you have to perform two searches, like to determine which region you have to go into, right? So that is why when you divide it into three parts, your search region becomes one third of the original search region. But now you have performed two operations instead of one.
Okay, okay.
Yeah. Anurag Jan asks, is this because the time complexity log n type? Yeah, this is basically the reason why the time complexity of binary search is log n, because at each step we are dividing the search region into half of its original size. So this is the time complexity, and you can see, as I mentioned, that also one more thing. This log n is basically okay. All right. So this is basically, I'm sorry, there's some issue with my phone. Please give me a minute. Yeah, sorry for that. Can you see my screen?
Yes.
All right. So, as I said, this time complexity is O of log n to the base 2. Uh, n is the number of elements that we have to go through, that we have to search. That is the size of the array or the search space. And it is base 2 because at each step we are dividing our search space into two halves. So first the search space is n, the next time it's n by 2, then n by 4, and so on till we reach 1. And it is easy to see that the number of steps involved is log n to the base 2. And this actually speeds up your operations really very fast. Like if you have to go through an array with 1,000 entries, you only need to perform 10 searches. And in case of like 10 to the power 6 entries, which is a lot of number entries in the array, you only need to perform 20 operations to find the number that you are looking for. So this is like extremely fast compared to the linear search. Now, where is it applicable? Which slide can you see?
Time
Time
complexity
com-
slide.
All right. So where is it applicable? So this as I told, that binary search algorithm is applicable where you have a linear, a sorted structure in your array. It is not necessary that it has to be sorted, because there are scenarios when it seems that your array is not actually sorted, but there is some structure that you can find out in your array, and that way you are able to apply this binary search. Now we'll see how what is this thing that we need to look for to see whether we can apply binary search to find something in the array or not. Now, before going to that, let's see what are the three commonly found types of binary search that we see. So one is the normal binary search. In this one, what happens is that we just need to find out whether some element is present in the array or not. So for this, this is the syntax that we use. This is an STL function. Oh, sorry. Here there is key as well, comma key, binary search, uh, begin and end pointers of the vector, and apart from that, key, that is what we are looking for. Now, if the key value that we are looking for in the vector, if it is present in the vector, it will return true. Otherwise, it will return false. So the output return type of this uh, binary search function is a boolean. For example, if the array is 1, 2, 3, 5, 6, and you apply binary search in this, if you pass the key value as 3, it will return true. And if you pass the key value as 4, it will return false. So this is a simple way, like this is a simple function, nothing complicated in that. Next is lower bound. Now, lower bound and upper bound, these are things which are like really very useful, and it comes up many times when you are solving problems. So it is like it is important to understand what actually lower bound and upper bound does. So what lower bound does is that it returns a pointer. Please note this thing. It's a pointer and not a value. It will return you a pointer to the first element in the vector or array which is greater than or equal to the key value. So if we see, let's say here is the syntax, lower bound. Again, same thing, same as the uh, syntax for the binary search. Only changes binary search is changed to lower bound. So lower bound, vector begin, vector end, and the key that we are looking for. So this time it will return a pointer to the first element that is greater than or equal to the key element. So if we say that our key element is 3, so what it will do is it will return you a pointer to this location, because this is the first element that is greater than or equal to the key value. If instead we would have asked for a key value as 4, then it would have returned 5, because 5 is the first element in the array which is greater than or equal to 4. Since 4 is not present in the array, it will return you the key value as it will return you the pointer of 5. And again, if you look for some value which is greater than the largest value present in the array, for example, if you look for 10 and here the largest element is 9, so it will return you vt dot end. That is the end pointer. And reminding that end pointer is the pointer in the vector which is after the last element of the vector. Is this thing clear? Like what I mean by pointer, and what I mean that when I say that it returns a pointer to the first element.
Yes.
What is VT here? VT dot begin.
Okay, so VT here is when I here VT is actually a vector. I've defined it that way. So VT is basically a vector of any type. Let's call it int, since we have used int in this example. VT. So VT is basically a vector. It is not necessary that you only pass a vector through it. Let's say you have an array, then you can also pass an array through this function. Like as I mentioned in previous classes as well, that what you do is that you pass the initial pointer and the pointer after the final element. So in case you have an array, let's call it ARR of size n, then you'll perform like this. Okay, sorry. If you have got an array, then what you'll do, you'll write like this: lower bound ARR, comma, ARR plus n. Why n? Because since there are n elements, so the pointer to the first element is ARR itself. The pointer to the last element is ARR plus n minus 1, because the indexing is zero based. That's why the pointer to the last element is ARR plus n minus 1. And since we need the pointer to the element which is just after the last element, it is ARR plus n. And then the key value. So yeah, it is not necessary that you only do it for yeah, sorry, it was causing some trouble. All right, so as I said that for here vector VT is a vector. And if you ask for the lower bound of 3, that is the key is 3, then you'll get this element. And if you ask for uh, might not- if you ask pass key value as 4, then it will return a pointer to 5. Now it is not necessary that you only pass vector. For arrays, you can write lower bound arr comma arr plus n and key. Yeah, also there was a mistake that you pass key value as well, which I missed here. Okay, so let's continue. So lower bound is clear to everyone.
Yes.
Okay, so
Yes.
all right. Moving on to upper bound, what upper bound does is that it returns a pointer to the first element that is greater than the key. So if you let's say pass key as 3, then you'll get 5. Even though 3 is present here and it is present multiple times, then also you will get the pointer to the element that is greater than the key value. And that's what is meant by upper bound. So this is the STL implementation for upper bound and lower bound. We'll see in detail how to implement it ourselves later in this lecture. So now let's see what a predicate function is. Now, as I said that whenever you are like making some uh, when you want to see whether you can apply this binary search algorithm for finding something in your array, there is something that you need to look for. So that is the predicate function. If you can find a predicate function for your array which satisfy a particular criteria, then you can easily apply binary search to that problem. What is a predicate function? A predicate function is basically a function which assigns a Boolean value to each element of the array. Let's say your array is A1, A2, A3, A4, A5 till AN. So don't be afraid. I'm sure like none of you must have heard this name predicate function. Uh, so it is nothing, but it is simply like when you apply f of a like to each element, it will assign either true or false to each element. Like it could be this way: true, false, true, true, false, true, this way. But if this is the case, then you cannot apply binary search to this. What is necessary is that the predicate function, there must exist at least one predicate function such that the mapping is like this. If false, 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 dot, 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 at some point there will be false, false, true, true, and then again all true elements. So if your predicate function is like this, that is the values it produces for each element is in this way, that first there are all false elements and the false values for like let's say till a of x minus 1 it returns false, and from a x plus 1 from a x to a n it returns true for all the elements. Then this then you can apply it binary search for finding this region, the dividing region, to find out that where this dividing region lies in your array. So in this case, you can find the dividing region using your binary search while using this predicate function. Is it clear what predicate function is? It is nothing much, but what it does is it basically assigns a false or true value to each element of your array. And using binary search, you can find this boundary where the values change from false to true, such that the predicate function is always like first it is all false and then it is all true. Is that clear? Any doubts in this?
Why do we have to do I mean, what is the application of it?
Uh, so basically, this is the condition which is required for binary search, uh, like to perform binary search in an array. So, like as I told you, upper bound and lower bound, these are not the only two possible scenarios where you can use binary search. There are like many possible scenarios where you can apply binary search if you can find a way to assign these values. Like uh, uh, the, if you can find a predicate function such that the it returns uh, false for the first x elements, let's say, and then true for rest of the elements. If like you can find any such function, then you can apply binary search to find the boundary where the false changes to true.
Sir, does it show that whether the array is sorted or not in a way?
uh, not really. I mean, it is not necessary that if your predicate function is such that ari is less than ari plus one, then this like it will it will not really. I mean, predicate function doesn't really tell you whether your array is sorted or not. Uh, and it is not even necessary for your array to be sorted to be able to find a predicate function which follow this property. For example, let us say mm, your array is like this: -1, -5, -3, -2, 0, 1, 5, 2, 1. So as you can see, this array, it is not sorted, but you know that in this array there is a property that at one point there is zero. Before that, all the elements are negative, and after
Okay,
that, all the elements
yes.
are positive. Yeah. So as you can see, if your predicate function is ari less than zero,
Then
sorry,
return false or
if
else true.
yeah, let's say if your predicate function is if ari greater than zero, then true, else false. So in this scenario, you can see that your predicate function will return false, 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 true, 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 true. So using this, you can easily find out where uh, uh, this boundary lies, where your elements turn out from negative to positive. So this is basically the necessary criteria for you to be able to apply binary search.
Okay, sir. Yes.
How we will apply binary search in this example?
Like what you uh, what you do is you can not use the this STL function for this scenario because it is implemented only for the sorted array. In this scenario, what you'll do is you will develop your binary search function in such a way that this is your predicate function. Like, and judging by the values written by the predicate function, you will perform the search. We'll see the implementation later on. So as of now, is this predicate function clear?
Yes.
Through this function, means through this method, can we find all the values in the array which are present at the correct position in ascending order?
Please pardon.
I mean, let us say the array is not sorted, but some values in the array are in the correct position. Means according to the, or if I sort the array, then the
Mm-hmm.
position of the element won't change. So can we
Mm-hmm.
binary search to get such elements like this predicate function?
Not really. I don't think you can do this using binary search to find out that which elements are there in the correct positions. Because again, like Um, I don't think you can do this because this is like a random array which I've provided, and there is no such specific property. This is just an example. Like in if there was some any random array, like the elements were mixed up in any order, then you cannot really find a predicate function which will tell you. And in fact, binary search is not binary search is a searching algorithm. It doesn't really tell you much about the properties of array, whether it is sorted or not. It you have to tell it that it is sorted or it has a predicate function which is sorted. That is, first you will get all false and then all trues, and you can find the boundary for that. So what you said, like finding out which elements are there in the right position, I don't think you can do this using binary search.
One more doubt. If the predicate function was like this, first five elements, let's say there are 20 elements. So first five elements are false, then next 10 elements are true, and last five elements are false. So here there are
Hmm.
two boundaries. So we can use binary search to find those two boundaries.
No, you cannot, because as I said that the necessary condition for binary search is that it should have only one boundary where false goes to true. And the reason is because as you said that there are four elements which are false, then true, and then false. So when you arrive at at any index and the value of predicate function is false there, you don't really know that where you have to search. Like you have to go to the left region or the right region, because if you are in the first half of the false region, then you have to search in the right portion. Whereas if you were in the right side of the false region, then you will have to look in the left region. So you are not able to decide where you have to go, because you don't know, like there's no such property which is existing here, which is there in the false true false region.
Yes, I got it.
Yeah. So moving on. In terms of predicate function, we define lower bound and upper bound in such a way that if you have got these as the outputs of your predicate function, and this is the boundary, then this is the lower bound, and this is the upper bound. Now, making it clear that this lower bound and upper bound is different from the lower bound and upper bound function that we saw here. The reason is that this lower bound and upper bound is defined in a particular way, and that is that in lower bound it will return a pointer to the first element which is greater than or equal to the key element, and upper bound is defined as returns a pointer to the first element that is greater than the key. So as you can see here, the predicate function itself is different. This is the hidden predicate function in this. Like the element should be greater than equal to the key, or great element should be greater than the key. So actually here, this is the predicate function for these two implementations. And as you can see, these two are different predicate functions. So this is basically different from the upper and lower bound that I'm defining here, because it only says that the lower bound is the element which is just before the boundary, and upper bound is the element which is just after the boundary. All right, and these two are defined for the same predicate function. And when we talk about these lower bound and upper bound, it is for sure that the upper bound will be the element just after the lower bound element. Whereas it is easy to see that it is not the case in this lower bound and upper bound implementation, as if you see for the case of 1 3 3 5 7 9, the lower bound of 3 is this element, and the upper bound of 3 is this element. So the difference is of 2 rather than uh, yeah, this element is 5 is the upper bound of 3. So here it is not necessary that the lower bound will be just one less than upper bound, because in fact it will be equal, the difference between the upper bound and lower bound in this scenario is equal to the number of the number of times that element occurs in the array. This is a very important property. I think I've discussed this before as well in some class. So this is something that you can really use when you want to find the count of any element in the array. So let's say you want to find out how many threes are there. What you can do is you can simply say count of 3 equals to upper bound of 3 minus lower bound of 3. So using this, you can find out how many elements are present in the array of value 3, in the sorted array, of course, because you can only apply binary search and these functions when the array is sorted. So this thing is uh, like pretty useful in many scenarios, because many times when you have to find out what is the number of times any element occurs in the array, you can directly use this line to find out the count. So remember this. That's clear, right? Any doubts like how these lower bound and upper bound are different from the previous ones? Here, the lower bound and upper bound are defined according to the boundary for the same predicate function, whereas those lower bound and upper bounds were basically STL functions, which provides a lower bound and upper bound only for a sorted array, which uh, for the particular key element. Any doubts in that? Or if you want me to explain it again, or is it clear? Anyone, please respond.
Clear.
It's clear? All right. So this is basically our definition for lower bound and upper bound. So let's not use the term bound here to avoid the confusion. Let's call it lower. This is not the correct term for this, but I'm using it here to make it clear. Upper boundary element and lower boundary element. So this is the term that we use here in this lecture to for this these elements, that is the element which is just before the boundary and the element which is just after the boundary. Now let's see the implementation of binary search. Here, this is the implementation of binary search which I copied from Geeks for Geeks. So what this does is that this implementation returns you the index at which any element is present. So what it does is that you pass the values of lower and upper index. Like I'm not going in very much detail for there are actually three implementations that I've shown in the slides, but I will not go in much depth because there's a better implementation which I follow, and it will be much easier to use this one because it can be generalized easily and it is easy to remember. So that is why I will discuss this one in detail. So I'll go through these implementations quickly and show you what it is doing. Yeah, so in this implementation, you can see that It is clear, right? Or is it visible?
Yes.
All right. I mean, is it readable for everyone, right?
Yes, it is visible.
Okay. So in case of here, we have passed the array in which we have to search the lower bound and upper bound as in the starting index and the last index for which we have to search in the region in which we have to search for our element, and integer x, that is the element that we have to search. So these are the four parameters passed to the binary search algorithm. Now, this is the if r greater than equal to L. So this is a recursive algorithm because it is calling back itself. Now, in this, can anyone tell me which is the predicate function by looking at the code? Is anyone able to identify which is the predicate function according to our definition?
If ARR mid greater than X.
Right. So this line, this is the predicate function that is being followed for this implementation. Now, based on this predicate function, this code is determining where it has to go. Whether if since we are looking out for x, now if a this line basically says that we have to run this algorithm when this condition is satisfied. That is because if it turns out that uh, this is actually hiding it. Huh. So here, this is also part of the code. So if R is greater than L, then we know that we have searched the region and the element X is not there in the array. So if this condition is not satisfied, that is R is less than L, then we'll return -1 because the element is not found in the array. And when R is greater than equal to L, when this will happen that L goes less than R, so let's say our region was initially 0 to 5. We our elements are 1, 3, 5, 7, 9. Now, since our elements are 0, 1, 2, 3, 4, and 5, there are 5 elements in the array, and we search in the region 0 to 5. So in this scenario, it will the value of mid will be 3. Not really 3. Here in this case, it is 2. Since mid is L plus R minus L by 2, so the value of mid will be 2. So it will check whether 5 is equal to 3 or not. Since we are looking out for 3, it will check whether 5 is equal to 3 or it is greater than equal to 3. It will find out that it is greater than 3. So it will reach in this portion where it is saying if ARR mid, where mid is equal to 2, because mid equals to L plus R minus L by 2. That is why here mid equals to 2 when we are looking in region 0 to 5. It will see that compare whether 5 is greater than 3 or is it equal to 3. Since it is not equal to 3 and it is 5 is greater than 3, where 3 is our key element, it will search in the region L to mid minus 1. That is, now it knows that 3 is present in this region only and it will simply reject this portion. Now it will search in region 0 to 2. Now it will check for this element. As you can see, the search region is divided into half, which is the property of binary search. Now it will see that the element is 3. So it will simply say that, okay, 3 is found and return the index of 3, which is 1 in this case, and the binary search terminates. But if the case was that instead of 3, we were looking out for 4. So again, from 135, the region would have further got divided into this portion, or rather, since we are not this portion, it would have been this portion, because it will check that 3 is not present, 3 is less than 4, so it should be in the region mid plus 1 comma r. That is, it will see in the region after 3, and that will give us 5. And since as this will continue, it will happen that eventually L will become greater than R, as just after this operation search in the it will search in region 0 and 2, 2 comma 1, and here it will know that our search region is extinguished, and we have not found the array, so it will return -1. So this is how this implementation works. What it does is that if it finds out the element, it will return its index. Otherwise, it will search in the rest half of the region. Is this clear?
Is there a specific reason why int mid is written as L plus R minus L by 2 and not L plus R by 2?
Yeah, there's a this is a good question. So what happens is that uh, when you are when you are using any implementation, there are many things that you need to keep in mind. That is, if instead of L plus R minus L by 2, you would have written R plus L by 2 in this scenario, then there is high chance that this would have either skipped the element, or it would have been in an infinite loop. The reason is that for any mid that if you have put mid equals to R plus L by 2, then what happens is that here you'll have to pass either L comma mid or mid comma R. Like, there are many things that you need to keep in mind. So because why this actually happens is because we are dealing in a discrete region, where in case of L plus R by 2 is let's say if L plus R is odd, then L plus R by 2 will give you an odd number, and like it will not give you I mean fractional region, because again this is integer division, and it will drop out the zero point 0.5 part. And that is why sometimes it happens that if you go for searching in region 0 comma 1, and in the next iteration again you will get 0 comma 1, if your mid is defined as mid equals to L plus R plus 1 by 2, then in this case the next searching region will again be 0 comma 1, and again in the next iteration it will like get fixed in, and it will get stuck in an infinite loop. And this is something which you will face if you try to implement binary search on your own. So that is why you need to keep a lot of things in mind, and it is suggested that you learn some binary search implementation, so that you do not face this issue, and you can directly use it uh, during the contest time, or like when implementing any code. Because otherwise, if you do not learn some implementation of binary search, and you try to figure out it at that time itself, then it might be possible that you face the situation that I just now described, and it will waste a lot of your time. So that is why I would suggest that you learn the implementation, and the one that I suggest you to learn is the one which I will be describing later on, because there are many merits associated with this one, and I'll discuss about it later. Again, next, if we see the implementation of lower bound, so this is the lower bound that we discussed before. That is in the beginning when we said that uh, in case of 1, 3, 3, 5, 7, the lower bound of 3 will be the element 3. And I mean, this is not the predicate function lower bound. This is the implementation for lower bound function, which returns a pointer to the first element which is greater than equal to the key value. Here, instead of returning the pointer in this implementation, it returns the index to that lower bound. So again, it goes on like similarly. This is an iterative function rather than sorry, recursive function. This is an iterative function, and here this is our predicate function. Oh, I'm sorry. This is our predicate function where if x is less than equal to ar mid, then high equals to mid, else low equals to mid plus one. So when you are uh, when you are writing whether you have to update high or low, what you need to see is that if your predicate function returns true, that would mean you are somewhere in this region, right? If your predicate function returns true, that would mean you are somewhere in this region, and you need to find out you need to find out your boundary, which will be in a lower region than the region you are currently in. The region in which I am is specified by the value of mid. The index mid tells in which region I am. Okay. So that is why if you see that the predicate function returns true, so you are in this true region, and that is why you need to reduce your region towards the lower half, and that is why you will change the value of high to mid. That is, if you were at this index, so now this will be your search region rather than the and the rest of the portion will be chopped off. And instead, if the case would have been that it returns false, then you are in this region. If it returns true, then you are in this region. If it returns false, then you are in this region, and accordingly you will take your decisions depending upon the value returned by the predicate function. That is, if it is true, then you will reduce it to the lower region, that is high will become mid, else your low value will be modified if you are in the false region. Why I am saying this? Because it is easy to remember the implementation this way, as this will help you to like determine for any particular condition of predicate function how you should modify the high and low values. So, like, this is the basic skeleton of binary search. You define a mid, you define a low and high index, which will be your endpoints initially, and you write mid equals to low plus high minus low by 2. In this scenario, you have written mid in this way. And as you can see, previously it was using high equals to mid minus 1 in the previous implementation, if you remember. So it was restricting it to mid minus one region, whereas here it is restricting to mid, and low is being restricted to mid plus one. And yeah, again, this is why I said that what you have to do here, like if you have to apply mid plus one or mid minus one, this is something that many people get confused, and that is why I'm suggesting the next implementation that I'll be showing, and I'll describe it in detail, so it would be easier for you all to remember. And so the basic structure is you define three variables: low, high, and mid. And you, in each iteration, while the condition that low is less than high is satisfied, you perform this iteration multiple times unless you reach at the position or the boundary that you are looking for. That is, if x, if your predicate function is true, then you reduce the value of high, or if your predicate function is false, then you increase the value of low, and that's how your region gets further restricted at each iteration. And finally, when you reach the end of the this while loop, at that point you will be pointing at an element which is the boundary element you are looking for, and you will return it. Is this clear?
The predicate function should return true when x less than ARR mid na. So
Right.
uh,
This is your predicate function. So if x is less than equal to ARR mid, then basically it is true. Otherwise, it will be false.
so here uh, on the slide that you have written, it should
Hmm.
be reverse, I think. First true, true, and then false, false should be there.
No. Okay. So you are saying that. All right. I get your point. So um, yeah. In this case, since there's it will be no. That's not the case. Like if your array is sorted, so let's say 1 3 5 7 9, and you look for 5, so initially it will be false and finally it will be true. 1 3 5 7 9, and you compare for 5, so 5 is less than 1, false, false, true, true, true. Here also the predicate function is following the same structure. Is this
Okay.
what you are asking?
Yes, I got it.
Yeah. All right. Any other doubts? All right, let's moving on. Upper bound is also pretty similar, because only thing that gets changed here is the this predicate function, and that is here it was x less than equal to ARR mid. Here it becomes x greater than equal to ARR mid. So this is the only thing that gets changed, and if you see, it is equivalent to saying x less than ARR mid, right? Sorry, ARR mid less than x, the other way. Like if you reverse it out, that is negate it. So okay, let me explain it again. So in case of lower bound, it was x less than ARR mid, then high equals to mid. What is done here? It is if x greater than equal to ARR mid, then low equals to mid plus one. Previously, high was being modified. Now low is being modified, and it is similar to saying if x is less than ARR mid, then high equals to mid, else low equals to mid plus 1. So now you can see how these two are similar. The only thing that is being changed is previously here it was less, previously it was x uh, less than equal to ARR mid, then high equals to mid. In upper bound, it is x less than ARR mid, then high equals to mid. And this is consistent with the definition where we said that the first pointer which is greater than equal to the key value will be returned in case of lower bound, whereas the first element which is greater than the key value will be returned in upper bound. The rest of the implementation is same here. Now moving on to the my favorite implementation, which I would suggest you all to follow as well, because it is easier to remember and it can be easily generalized, because instead of like saying which is our well what is our predicate function, we use a generalized predicate function for this. So this is the implementation. Now what we do is that in this implementation, uh, we pass the low and high values along with the key. Here I'm not trying to explain you the implementation of binary search, but I'm trying you to remember how this implementation is, how to remember this implementation. So first of all, the necessary thing for this implementation is that if you are searching in the region 1 to n, that is, if you are searching in the region 1 to n, you need to pass the low value as 0 and high value as n plus 1. That is, if you are looking for some element in the region L comma R inclusive, including L comma R, then you need to perform this binary search over the region L minus 1 comma R plus 1. This is necessary for this implementation, as I'll discuss later why. Now, what this does is, in this binary search, is causing some issue. Can everyone see? Can everyone read what is written? Is it visible
Yes.
and readable?
Yes.
All right. So here what we do is that we pass low, high, and key. These are the three parameters that we pass: low, high, and key. Now we define our L equals to low, H equals to high, and we define mid as high plus low by 2. Remember that here we will not be using any plus 1 or minus 1 as we saw earlier, like low was assigned as mid plus 1 or high being assigned as mid minus 1. Instead, we simply write mid equals to high plus low by 2. Now, uh, till when we run this algorithm, this iteration, until h minus l is less than equal to 1. That is, it will terminate when h minus l becomes 1. That is, l equals to h minus 1. When this condition happens, then this iteration terminates. So when this iteration terminates at this location, l equals to h minus 1, this thing happens. We'll discuss further why this is useful. Now let's see what happens inside. Inside, if predicate function is true, then h equals to mid, else l equals to mid. So this is again the same thing as I said previously. If your function is true, then you are in the true region and you need to go this way. That is why from high, which was previously here, we will shift it to our new high location. If we are in the true region, that is predicate function returns true for mid. Uh, we better if I write predicate function of mid. If it returns true, then we are in the high region, in the true region, and we need to shift our high region towards the left. And our new high value becomes equal to mid. And in case of false, the opposite happens. That is, our low value becomes equal to mid. And again, we'll update our the value of our mid variable. It gets updated in this line, and this iteration keeps on running. So what are the key points here? We first of all, it is necessary that we pass L minus 1 comma R plus 1 if we are searching in region L comma R. That is, if it was 0 comma N minus 1 inclusive, then we would have performed binary search for minus 1 comma N comma key. So please remember this. This is necessary for this implementation. L equals to low, H equals to high, we assign our variables, and our mid value is defined as high plus low by 2, and then this while loop runs until the difference between h minus l becomes 1. Now here comes the interesting part. Why this implementation is beautiful? Because the value of l at the end is the lower boundary and the value of high is the upper boundary. So you can simply return L if you want the lower boundary. What is the lower boundary? As I discussed before, if this is the boundary, this is the lower boundary element and this is the higher boundary element. So you do not need to remember different implementations for this thing. You can simply return L if you want the lower boundary, and you can return H if you want the upper boundary. So I would suggest you all to learn this implementation, or if you find any other implementation easier to learn and to use, then you can learn that, and please solve some problems use of implementing binary search so that you get hold of it. Because like even I myself have faced this many times, that what happens when I'm coding binary search, and in the beginning I was figuring out what high will be and what low will be while implementing, and it resulted in like a lot of mess. Because if you are using this implementation, for example, uh, if you are using this implementation and instead of low equals to mid plus 1, you write high equals to mid plus 1, or you write high equals to mid minus 1, it will get messed up, and you will either miss the value that you are looking for, or you will be stuck in an infinite loop. And these are the small things that you need to keep in mind while using any implementation of binary search to avoid these infinite loops. And that is why I'm suggesting to follow some particular implementation and learn it by heart, and by implementing many problems using that implementation. So, is this implementation clear to everyone, or are there any doubts overall from binary search algorithm which you have not understood?
Can you please explain that remember part which is written at the bottom?
Yeah. So remember part is basically it says that for this particular implementation, like if you look for this implementation, and in this previous implementation, the when you are calling this function, you need to pass the value of L and R. So in some implementation, it requires you to include the last element. Like some implementation would require you to perform binary search over 0, comma n minus 1. Some will require you to pass 0, comma n for the same region. Like the endpoint is inclusive or non-inclusive. So these are the things that different implementation requires you to pass when you are looking for when you are searching for some element in an array. And for this implementation, this is the condition that is required, that if you are looking in region L to R, if you are looking in region L to R, where L and R are inclusive, then you need to perform binary search over L minus 1 to R plus 1. This is the necessary requirement for this condition. That is, when you are calling that function, you need to pass the low and high values as this. For example, if you are calling for the region 1 to n, okay, let me write it here. If you are calling for the region 1 to n inclusive, then you will call binary search in the region 0 to n minus n plus 1. That is less than one element less than 1 and one greater than n, 0 and n plus 1. You will perform the binary search in this region. This is the requirement for this implementation of binary search. Is that clear?
If we have to find the first element, so if
Hmm.
we use 1 to n, then it will not give the lower bound. So that's why we are using 0 and n plus 1.
Right. So in that case, if your predicate function returns this way, true, 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 then your boundary is here. And since this is your first element, and so in this scenario, the lower bound should be, okay, it might be confusing if I write it here. So if this is your array 1, 2, 3, 4, 5, and for all elements it is true, so your lower the boundary is before the first element and your lower bound should be 0, right? Because here it will be your lower bound and this is your upper bound. That is why we are passing 0, like 1 less than the starting value and 1 greater than the ending value, so that uh, 0 can be equal to lower bound. And in the opposite scenario, that is when there are all false, then your high value will be after the last element. And this is the reason why we are calling it from -1 to n and not from 0 to n minus 1. Is that clear? Is this what you are asking, Shwansh?
Yes.
Yeah. Any other doubts from anything anything that I taught till now in the session?
I wanted to ask what will be the difference when we write L plus R by 2 and L plus R minus L by 2, as it will give the same answer for mid.
Can you please repeat?
When we are writing mid equal to L plus R minus L by 2, if we directly write L plus R by 2, then what will be the difference? I didn't get that point.
In this scenario, in this implementation, you are saying?
Yes.
Yeah. So like you can try this out in your system that by replacing this low plus high minus low by 2. Instead, you can write high plus low by 2, and you will see that it will eventually get stuck in an infinite loop most probably. The reason is that this by 2, like if you write mathematically, it will obviously be this. If you write mathematically, then low plus high minus low by 2 is equivalent to low plus high by 2, but this is true mathematically. What happens is that when you perform this operation in a computer, this division that you see here, high minus low by 2, this division is integer division. So here 5 by 2 is also equal to 2 and 4 by 2 is also equal to 2. And this is what causes issues. Like, let's say in this scenario, if your low equals to 0 and high equals to 2, then rather if your low equals to 1 and high equals to 5, so what will you get in
Both will give 3.
give 3? If okay, so in this scenario both will be giving 3 as the output. So I guess, yeah, you can replace this uh, replace this thing with high plus low by 2 for any other value 2 plus 2. Yeah, I guess you can do this. You can replace this. It will not cause issue here. But sometimes some implementation are like in some implementation you need to define your mid equals to low plus high plus 1 by 2 for it to work, because in case of low plus high minus 1 by 2 it will get stuck in an infinite loop. So in those implementations you cannot do this.
Okay.
Any other doubts? Okay, then we'll move on to sorting. So this is these are we have discussed before that for sorting there is a sort function in STL where you pass the initial pointer and a pointer after the last element, that is the initial begin pointer and end pointer in case of vectors. And there was one third argument which we discussed, which was uh, a non-necessary argument, like you could leave it empty or you can pass it, which is the comparator function. And this comparator function tells the algorithm, the sort implementation of sort function of STL, like what comparison it has to follow for this for sorting this array. So now today we'll be discussing about this comparator function. Now, as I said before, for sorting an array in descending order, you simply use this greater LL. Here, LL can be replaced by int. LL is basically something that you use for long int in CP. So that's why I wrote it LL by mistake. In case of integer array, you can write it like this: greater in this triangular brackets int and bracket open bracket close. So this is the implementation for this is what you write for sorting the array in descending order. And now in case there is no such comparator function like greater available for some data structure, like for example some custom data structure that you implement yourself, and you want to sort it in a custom way, that is using this custom comparator function, you can do this. So as we saw that in here we don't really have any such implementation in STL for any custom predicate function. But luckily for sorting, we have this implementation where you can specify what comparator function you want to use, and in that way it will sort the data structure. It will sort your array for that data structure. So basically, what this comparator function does is that it returns a bool value, and this basically tells the function to like what is the comparison basis for the elements of that array. So as for integers, it is known that if one is less than one, and if you compare one and two, so in case of integers, we know that for comparing one and two, we know that one is less than two. Now, if I say that there is struct A, any structure, struct, let's call it NT. Now there are two elements of type struct NT, A and B. Now I ask you, what is the way? A and B are both custom structures, and now I ask you how to compare them. So of course the compiler doesn't know how to compare them. So that is why you have to specify the compiler what is the comparison basis of these two comparison basis for these elements of this structure, and that is you specify this thing to the compiler using your comparator function. And as I said, it is useful when you have your custom data structure. So let's see through an example how to implement a custom comparator function. So let us say you have a structure, let's call it point, and it has two elements, one integer x and another integer y. You can draw it an analogy with geometrical x and y coordinates in a graph. Now uh, you have an array, and now you want to sort the array of these points in such a way that it first compares your x values, and then if x values are same, it will sort it according to the y values. For example, if your points are 1 comma 1, 2 comma 1, 2 comma 2, so this is the sorting you want. Like first it will see the x values, And if so in this case 1 is less than 2, so this element will come first, 1 comma 1 will come first. And in case of 2 comma 1 and 2 comma 2, since 2 is same, you compare the y values, and the y values are 1 less than 2. That is why this will be the order in this uh, for these three elements, and which is basically an array of points. Now if you want to sort out an array of points of point, which is a custom data structure, you define a comparator function in this way. And what you do is that this is a comparator function of return type bool, and you pass point A and point B to the comparator function. These are point A and point B are basically the structure that you are passing, your custom data structure, and you define the custom custom comparator function in such a way that you compare if a dot x and b dot x are not same, then return a dot x less than b dot x. Otherwise, return a dot y less than b dot y. So you simply need to do this, that you need to specify how to compare to custom data structures. So that is what this comparator function does. It's not necessary that it has to be named COMP. Of course, you can name it anything you want. And so basically, this is the basic behind this comparator function. And let's say instead you wanted that instead of this order, you wanted it to be sorted in this order. That is, if the values of x are not same, that is basically if values of x are same, then y should be in increasing order. Sorry, y should be in decreasing order. That is, since in 2 comma 2 and 2 comma 1 the x values are same, so the y value should be 2 then 1, that is in decreasing order. So you could have changed this line into b dot y less than a dot y. So basically this custom comparator function gives you this opportunity and this freedom to toggle how your structures are being compared. In this case there were only two variables in the structure. Let's say if there were many, let's say uh, three variables in this structure, then you could have defined your order accordingly, like first comparing x then y then z, or first comparing x then z then y. So this is basically the freedom that this custom comparator provides you with. So the necessary thing about comparator function is that it should return a bool for comparing between two variables of the same type for which of the array that is being sorted. Like if the array is of type point, or if it is of any other data structure type, this comparator function should accept values of the same data type as its parameters. As in this case, here point is being accepted if you are sorting an array of type point. Let's say I define an array point, let's call it grid, of size 10. Now here I initialize the values of the elements in the grid array. And now when I want to sort it, I'll call it this way: sort grid, comma, grid grid plus 10. Nothing new till here. Next thing is COMP. That is the name of our comparator function. Remember, you do not add curly braces after COMP. You just write the name of the function. You do not write it this way. This is wrong. This is the right way to write. You do not include the curly braces, the brackets after the name of the comparator function. Everything clear till here? Like how to define a comparator function?
Yes.
And how to implement it so that it returns. Basically, it tells you the ordering of the elements of the array that you want to sort. Is that clear to everyone?
Yes.
All right, moving ahead. Now, this is the most important thing which the comparator function needs to follow. Like, if you mess this up, it will give some random undefined behavior that you will like spend a lot of time figuring out why this is happening, and that is basically because of the comparator function defined in a wrong way. So always remember this key important point when you are implementing your comparator function. That is, it should always return in, it should never be defined in such a way. That is, you are writing a dot x less than equal to b dot x. The reason is, if you, let's say, let's call two elements a1 and a2 in this array. Now, when your comparator function will call a1 and comp a1 and a2. Let's say there are two elements in your array, a1 and a2, and both are equal. All right, a1 equals to a2. What will happen is that when you call comp a1 a2, then this will give you a1 less than equal to a2, right? And that is true. So it will return you true. What about comp a2 a1? This will also return true. So this is something that causes issue with the implementation of the sort function, that in case of inequality, it should return false, not true. And if you do this, like there's some, if you ask me the reason, there is some complicated behavior behind the implementation of sort function, and it is a requirement of the sort function that the comparator function should follow this property. If you want to read more about this, I will post the link in the in in the discussion for a blog which you can read to understand what exactly is happening behind the scenes. So this is the necessary requirement, that it should never be in this form, that a dot x less than equal to b dot x. Rather, it should always be defined in this way. Here, if you compare two equal elements, a1 comma a2, it will return false for both scenarios. And in this scenario, it will run perfectly. Otherwise, it will give very random behavior, and the array that you will get for this implementation will not be in sorted order. The array that is returned after calling this sort function from this implementation of comparator function, it will not be in sorted order. So always remember this thing, that in your comparator function, you do not include this equality sign. Is that clear? Yeah, also by equality, I do not mean that this is legal, a dot x greater than equal to b dot x. This is also not legal. You have to keep it this way, such that it is less than sign and not less than equal to sign. Is that clear? Or any doubts in this?
Yes.
Anyone else having any doubt in anything that is taught today? All right. If no one is having any other doubt, then we can close the session. I would say for this week, you guys can devote your time to practice problems on binary search. And for this comparator function, there is not much. You can try to implement this comparator function for any custom sort, uh, custom data structure that you want to sort. And please implement it once so that you get used to this. Uh, yeah, one more thing was that remember this thing, right? You do not include curly braces here. Sorry, you do not include the brackets here. You write just the name of the function and not the brackets along with it. And yeah, please practice some questions of binary search and sorting with comparator function so that you get hold of it. And yeah, please remember, if you just watch these lectures or attend the lectures and you do not do any practice on your own, you will not be benefited much. Like you'll get hold of all this stuff only when you get down and start actually practicing it. So yeah, please practice problems so that you get a better understanding of these concepts. Okay, so if no one else is having any other doubt, we can close the session.
Can you share the slides after the class?